we're going to be talking about sample spaces and start to talk about probability in statistics today. All right, so first question is, why is probability involved in statistics? And then we're going to talk a little bit about some probability fundamentals, and then talk about what is a sample space. And from there, we're going to talk about how to make sure we cover the entire sample space. We don't want to leave any holes. And there we're going to introduce the fundamental principle of counting. And then we're going to talk about where do the probabilities come from? How can we check whether our model matches the real world, right? So we might have a probability model, right? But how do we know whether that model is any good? And there we're going to invoke the law of large numbers. Okay, first, why the heck are we talking about probability in statistics? Well, you know, statistics is all about samples from a population, and we never really know what that population is like. But we have an idea of what that population is like, and we call that a model, right? We call it a model of the population. And we want to know how likely is a particular sample, the empirical data that we have, the stuff we actually collect, how likely is this given a particular model of the world, a theoretical model, or, you know, theoretical population, right? And so whenever you compute probability, you're looking at some subset over the total number of whatever you have, right? So in this case, in probability of statistics, we're looking at how likely is a particular experimental outcome over all the different kinds of outcomes that we could potentially have had, right? So we need to have a model of the world to figure out this total, right? Model generated. And that will give us the probability or the likelihood of our experimental outcome. So let's start off with a little example, just a little case that might be helpful for us to wrap our minds around. So I like to drink El Cheapo coffee, because I just add like sugar and milk and stuff. But I want to know, well, can people tell the difference between like El Cheapo and expensive coffee? Can they tell the difference between cheap and gourmet? Like there are those really expensive brands, and they even have coffee where apparently it's like monkeys like eat the coffee bean and then they like poo it out, and somehow like the enzymes in the stomach make the coffee bean like better, and so this is like one of the most expensive coffees you could buy, right? Sort of sounds gross, but it's supposed to be really awesome. And it just makes me wonder, is it really awesome? Can people tell? I actually always wonder this about really expensive like wine as well. Can people tell that it's expensive or not? So one model of the world we might have is that these people are all just chumps and they're just guessing, right? They can't tell the difference. They're just guessing between gourmet and cheap coffee. And what it really is that when you go to Starbucks and pay and it's really nice and they have music and it's dark and you have a scone, then that coffee just tastes better than maybe McDonald's coffee, right? So maybe that's it, right? So maybe when people actually taste the coffee, they're just guessing. That might be one model. So let's say we want to do a taste test with 100 coffee drinkers, and we just give them little cups of in the same cup, it looks like the same thing, and one has really expensive coffee in it, and the other has cheap coffee in it. So let's say we have an N of 100 people, 100 taste testers. Let's say no one can actually tell the difference. Does that mean everybody will get it wrong? So we'll have 0 out of 100 people correct? Probably not, right? Even if they're just guessing, we'll probably have something like, it might be reasonable to expect something like about 50% of people being able to tell the difference or guess correctly, right? So we might see 50 out of 100 correct, right? And that would be pretty reasonable, right? Still reasonable to assume model, right? But let's say 90 out of 100 people got it correctly. That would probably be really hard to do if everyone was just guessing, right? So, if it's 90 out of 100. Oops. Correct. And sort of difficult to see the model as being likely. Model may be wrong. Right? So in that way, we could look at the data that we have and see whether our model seems likely or not. But let's say everyone can tell the difference. Everyone can actually tell the difference. Well, does it have to be 90 out of 100? Could it be 89 out of 100, right? Could it be 88 out of 100? 70 out of 100? 60 out of 100? Where do we draw the line for where we say, oh, yeah, people can tell the difference, right? And if we saw that only 50 out of 100 got it correct, would we say that this model is likely? Well, here we might say model is more likely than this scenario. Right? So if everyone can tell the difference, this might be a more reasonable empirical data to see than to see this, right? This would be like, oh, we wouldn't expect that. So, so in that way, it's important to know the probabilities of these different outcomes, right? So how likely is 50 out of 100? How likely is 89 out of 100, right? And is one more likely than another given a particular model of how the world works? All right, so in order to create a probability model, we want to talk about a couple of different little basic things to help us get better, to help us get on the same page about probability. So as we've talked about before, when we talk about probability of some outcome, we usually talk about it as P of C, right? So this might be the probability of being correct. And maybe we'll just start with one taster to make it easy. So the probability that one taster is correct, given that everyone's just guessing, maybe we'll say 50%. Right? There's only a 50% chance that they'll be correct. And the probability of them being incorrect might be the other half, right? Now, correct and incorrect are what we think of as disjoint events. You cannot be both correct and incorrect at the same time, right? You can only be one or the other. We also call that mutual exclusivity. And so because we have disjoint events, these probabilities should add up to 100%. And you can only be correct or incorrect, right? So that's the only two zones of the space. So we've covered the whole space, and it adds up to total probability of 1. And that's how probabilities always work. If you've covered the entire sample space, that entire sample space's value is 1. How about two tasters, right? How about if we had two tasters? What is the probability that both of them guess correctly? Well, it's helpful to think about what is the entire sample space? Like, what are the different scenarios we could have? Well, we could have number 1 tastes correctly and number 2 tastes correctly, right? That's the event that the outcome that we're interested in. But there is a chance that 1 might get it correct, but 2 doesn't. There's also the chance that 2 gets it correct and 1 doesn't, right? So there's all these different outcomes, right? And it would be helpful if we could figure out the entire sample space and assign probabilities to each zone of that sample space. How do we do that is the question. Well, that is actually a very old question. In the 1700s, there were two mathematician guys. One guy is this French guy. I think you say his name like D'Alembert or something French-like, and Necker, a Swiss mathematician. And they sort of had this argument about, okay, what is the probability of flipping 2 heads in a row? And that's sort of similar to this idea, what's the probability of getting 2 correct guesses from our tasters, right? So, it's the same problem. It's what we call isomorphic. They have the same structure. Well, D'Alembert was saying, okay, well, there are 3 different situations you could have. One situation is that you could flip heads. First flip, heads. Or first flip, I mean tails, right? And that's not what we're interested in. We're interested in 2 heads, right? There's another possibility that the first flip is heads, and the second flip is also heads, right? And this is what we are interested in. And there's another possibility that the first flip is heads, but the second flip is tails, right? And that's also not what we're looking for, right? So in D'Alembert's model, we have these 3 situations. The first has the number of heads as 0. The second has number of heads as 2, I'll put that down here. And the third has the number of heads as 1, right? And so in D'Alembert's model, each situation has a probability of 1/3. And if you add them all up, you'll get 1, right? The whole sample space. And so he was pretty proud of himself. But then Necker came along and said, brother, I think you left out something. Because situations where the first flip is tails should be symmetrical. That should be equal to all the situations where the first flip is heads. I don't know why you have the first flip being heads as being more likely, right? Because if you add these 2 together, that's 2/3 versus 1/3. Why is that more likely than the first flip being tails, right? That doesn't make sense. So Necker said, okay, I think the sample space looks like this. First flip tails, second flip heads. First flip tails, second flip also tails. First flip heads, second flip heads. This is the one we're interested in. And first flip heads, second flip tails, right? So if you look at this, the number of heads, that's being 0, that's this one, right? So in this one, that has a 1/4 probability, 1 out of 4, right? Having 2 heads, right, that's the one we're interested in, that is this one, and that's also a 1/4 probability. But there is 2 different ways where you could have 1 head, right? 1 head, the other one being tails, right? So there's 2 of them, and so that would be 1/2. And if you add all these up, you get a total of 1, right? And so Necker argued, this is the right probability model, not this, right? And so they wrote papers about this. And yeah, there is I hope you could see, there is sort of a problem with D'Alembert's model. One issue with his model is that he didn't make a complete list of all the different outcomes that he could have. And all possible outcomes, that's what we mean by the entire sample space, right? So if you had all the possible outcomes, all these different zones, right, then you would cover the entire sample space, and that space will equal to 1. Problem with D'Alembert is that he's missing some of the possible outcomes. But Necker got it right. He listed all the possible outcomes that could happen. So the sample space is the complete list of all disjoint outcomes. And remember, disjoint means, another way of saying it is mutually exclusive. That means no 2 disjoint events can happen at one time simultaneously, right? You can only have one or the other. And all of the outcomes in a sample space must have a total probability equal to 1. So each of these outcomes must have a probability of somewhere between 0 and 1, right? If some event, like event A, has a probability of 0, this means there is no chance of this ever happening, 0, right? If we have another event that has the probability of 1, that means it's going to happen 100% of the time.